Okay, so I think we're ready to get started. So welcome to our last day, Friday, and our first talk will be by Jacob Campbell, who will tell us about commutators in finite free probability. And just remember, if you want to ask a question, get my attention, and I'll bring the microphone over. Otherwise, Jacob won't be able to hear you.
Great. Thanks for the introduction and for the invitation to speak here. Um, so yeah, so this talk is going to be about a preprint that I posted, I guess last fall, on the problem of describing commutators in the context of finite free probability. So I'll just kind of like review what this is, even though we've heard a bit about it this week. But yeah, so my notation here, because like the theory is about expected characteristic polynomials. And so my notation for a characteristic polynomial is this like C with the like the variable is the little x and the big X is the matrix. And it turns out that you can arrange this polynomial like at the level of coefficients in terms of these symmetric functions in the eigenvalues. So like this ek of x, this means right, well, basically it means this. Right, so this is like the elementary symmetric polynomial in the variables x. And so these are the coefficients of the characteristic polynomial. Another bit of notation is the unitary group. So UD is the group of D by D unitary matrices. And this has a unique invariant probability measure called the Haar measure. And so when I say random D by D unitary matrix, I mean random element of UD sampled according to this Haar measure. Yeah, so the starting point for finite free probability is this result of Marcus, Spielman, and Srivastava, where they kind of, well, they realized that the expected characteristic polynomials of like these sums and products of randomly rotated matrices. So like here, A and B are fixed deterministic D by D matrices. So they realized that these sums and products behave in some ways like finite versions of the free additive and multiplicative convolutions in free probability. Of course, it's very well known that at the level of like average eigenvalues, these converge to basically to these operations. But it turns out that the expected characteristic polynomials display some behavior similar to these, but like at a finite level. And so their result is easiest to phrase in terms of coefficients. So like, these are the coefficients of the characteristic polynomials. Right, so the first one is that for the sum, basically the expected, kth coefficient of this characteristic polynomial has this kind of like binomial sum form. Right, so it's like a sum over, I plus j equals k of like the ith coefficient times the jth coefficient with some normalizations. And then for the multiplication, it's actually much simpler. It's just, directly multiplying the coefficients and then normalizing by binomial. Yeah, and so these describe these expected characteristic polynomials of sums and products. And so once you know sums and products, then maybe the next natural question, especially if you know a bit about free probability. Actually, no, I should make this definition first. So we have like, this result about, sums and products of random matrices. And so we can kind of build this into a definition of of operations on polynomials. So like if you have two polynomials, P and Q, and you kind of arrange their coefficients in the way that we did for the characteristic polynomial, then you can kind of like turn this theorem into a pair of definitions, right? So you just, for box plus subscript D, you put like the P's and Q's together, exactly the way that you did with the EKs here. And then you can put the P's and Q's together for multiplication, again, in the same way that we did in this theorem, right? Just multiplying them and normalizing. And so these two operations, of course, are completely algebraic, right? There's no like analytic content to this definition. And it turns out in this form, these operations were already studied about 100 years ago, specifically 101 years ago in 1922. Of course, without the random matrix interpretation, but they were interested in these because these have nice properties related to preserving real roots. So for example, if P and Q are both real rooted, then this polynomial is real rooted. And then there's a similar result for multiplication, where like if P and Q are both positive rooted or maybe non-negative rooted, then so is the box times of them. So that's why I think Walsh and Sego were interested in these. But yeah, so this theorem is basically recovering these old operations on polynomials. Right, and so now once you know about addition and multiplication, maybe the next natural question is when you combine them in like some simple way. So for example, if you take the commutator, right, of like A and UB U star, then how do you describe the expected characteristic polynomial in terms of the individual characteristic polynomials? So this is, I guess you could say, is kind of the next natural question after like sums and products, especially if you know about the history of free probability. This was solved in free probability using free cumulants in the 90s. So, right, so the answer is the main theorem from this paper that I'm presenting. So if you have two polynomials, like P of X is the characteristic polynomial of A, and Q is the characteristic polynomial of B, then the result is that the expected characteristic polynomial of the commutator has this form in terms of like the individual polynomials, right? So there's like a part where it depends on P. So this is kind of like I'll explain this later, but this is kind of like a symmetrization of P. So like this polynomial, this has like all like basically its odd coefficients are zero. So it's like even in a certain sense. And then so is the dependence on Q. And then there's this other polynomial, which I call Z, which like you can write down specifically, and I'll do that later. But I don't think it's really relevant what this is for now. But the point is that this Z is just like a sort of universal polynomial that doesn't depend on A or B. Right. So, and then I'm gonna make this notation with like a square subscript D for this expression, right? So like this again is just like an algebraic expression involving these polynomials. So I'll use this as shorthand. And this is inspired by the paper by Nika and Spiker from 1998, where they solved this problem in free probability. This is the notation that they use there, except without the D, of course. Right, so just a few things I want to point out in general about this result. So the first one is that this expected characteristic polynomial of the commutator And actually, I should mention this I here. Um, this I is meant to make this matrix self-adjoint. So in free probability, um, this is commonly used when studying the commutator because it's just convenient to make it self-adjoint. And so here, I'm also using it so that like this characteristic polynomial, like for each fixed u, is real rooted. And I'll kind of explain why that's relevant in a little bit. But for now, I want to point out that, so based on this result, right, this expected characteristic polynomial of this commutator, it only depends on P and Q through these expressions like P box plus P of minus X, and then similar for Q. And so basically this is like a way of taking just any polynomial P and getting rid of the odd coefficients. So yeah, this is one kind of parallel with the situation in free probability, because in free probability, there's basically the distribution of the commutator of free elements is only going to depend on like the even cumulants, right? Like the odd cumulants basically cancel out, and so this kind of parallels that aspect of what happens in free probability. And then the other parallel with free probability is that, again, this expression back here, this shows that the odd coefficients of this expected characteristic polynomial are 0, or like, oh, what happened? Yeah, it jumped around, sorry. Yeah, so the EKs for odd K are 0. So basically the expected characteristic polynomial, like this, has this form, right? So it only has so the roots are basically like symmetric around the origin. And so this kind of parallels the fact that free commutators are even. So these are just two general points that I want to make about the result. And to be a little more concrete, I want to show some examples of what this result says. So in this paper from 1998 by Nika and Spiker, one of their first sort of examples of how they use the result is they show that if you have free elements A and B, and you assume that B, the distribution of B, is this like even Bernoulli, so it has like 1/2 mass at plus or minus 1, then the distribution of this commutator of A and B is just the distribution of A box plus the distribution of minus A. And so this is something that you can easily test using polynomials and a computer. So here, these graphics are all done in Sage. But so if you set D equals 40, so that's reasonably large, and you let P be the polynomial whose root distribution is this. So 1 with multiplicity 20 and a root at -1 with multiplicity 20. Then when you put my formula into the computer with this polynomial, so like with, P equals Q here, and you do the commutator, this is the histogram of the roots that you end up with. And so you can kind of compare that with free probability, right? Because if in this result you also let A be like have the same distribution as B, then this formula is going to give you an arcsine distribution, right? Because it's just free additive convolution of two Bernoullis, which is arcsine. And so this orange line is the density of the arcsine distribution. So you can kind of see that the root distribution is approximating the arcsine distribution. So this is one example. And then also on the other side, if you do this in finite free probability, so this is like taking P box plus P, box plus D with P, then you get a slightly different set of roots, but they do have essentially the same distribution, right? Like you can see maybe in like the middle, there's a little bit of a difference, but overall it's still very close to the arcsine distribution. And so this is exactly what you would expect if you want finite free probability to kind of converge to free probability. And so this example, I think, kind of illustrates that it's on the right track. And then another example from this paper by Nika and Spiker is if A and B are free semicircular elements, then they're able to compute the commutator. It's a very complicated density function, but I think the simplest formula that they managed to write down is this R transform. And then basically they use this R transform to solve for a much more complicated density function. And so that density function is in orange here. And then the histogram is taking two Hermite polynomials. So these are kind of known to be the finite free version of the semicircle distribution. This is kind of known from papers by Marcus and by Arizmendi and Perales. And so if you put these polynomials into the computer and find their commutator, here D equals 60, and it's already pretty close to the right density based on free probability. So yeah, these are just a couple of examples to show very concretely what my result is doing. So does anyone have any questions at this point?
Yes, we do. Just hang on a second.
Sure.
So the microphone is very directional. You have to.
Okay. Yeah, maybe I missed something. So you're saying you have a result to the effect saying that the root distribution of this anti-commutator converges to the free probability one?
So yeah, I'm not saying that I can prove that. I'm just kind of giving some examples that suggest that that's true. And I'll say more later about why it's not so easy to prove that so far. But yeah, like so I'll just say now that I don't have a proof that it converges to free probability, that it converges to the free commutator. Sorry.
Okay, thanks.
Yeah.
Wait, please continue, Jacob.
All right, thanks. Yeah, so these are just a couple of examples, but what I want to kind of do is for the rest of the talk is explain how this result is proved, because it's using kind of a wide range of techniques that I don't think have really been used very much before in this area. Or I mean, some of them definitely have, but there's a little bit of novelty here. So basically, most of the work is in reducing this analytic problem, right? Because we're computing some expectations over the unitary group. And so most of the work is in reducing to a combinatorial problem. And so, first of all, the techniques here don't actually depend on self-adjointness. So we can ignore this like I here in the commutator and just work with the, like the direct commutator. So like A times UBU star minus UBU star times A. And this is okay because these coefficients, like when you multiply, the matrix by I, that just comes out of the coefficient as an I to the K. So, this is just going to be a sign basically, like as long as the Ks are even at least. And right, so we can just work with this. And another reduction, like another very simple reduction, is that since Haar measure is invariant and characteristic polynomials don't change when you conjugate by a unitary, we can assume without loss of generality that our matrices are diagonal. So we'll assume that A is the diagonal matrix with entries A1 through AD, and similarly for B. And I mean, maybe this isn't really a reduction, but up to a certain point, we might as well work with this kind of linear combination of A UBU star and UBU star A. So we can introduce some like formal commuting variables, Y1 and Y2, and work with this expected characteristic polynomial. And this, so there's a certain point where we really do want to take Y1 equals 1 and Y2 equals -1, but I think it offers some insight to like see exactly where that point is, where you need to assume that you're working with the commutator. Right, so yeah, so here's basically the outline of the proof. The first part is to use this so-called Weingarten calculus to turn the analytic problem into a combinatorial one. And then the combinatorial problem that you get from step 1 will still be very complicated. So steps 2 and 3 are more reductions. But let's just focus on 1 for now. So, right, this is the basic expression that we're working with. It's the expected kth coefficient of the characteristic polynomial of this matrix. And so when you sort of untangle this in terms of matrix entries, you get these very complicated formulas, but the integrals are like these integrals of matrix entries, right? So Uij, this is a function from UD to the complex numbers, which picks out the ijth entry, right? So we're basically integrating products of these and their conjugates. And so, these are indexed by a bunch of things. There's like basically the sums on the outside here that I'm kind of skipping over. These include like sums over subsets of, 1 through D, and then permutations of these subsets, and then also multi-indices indexed by these subsets. But we can just focus on the matrix part, like the integration part, just for the sake of readability. And so basically we need a good tool for integrating things like this. And so this is called Weingarten calculus. It's a very good way of handling these integrals. So in this form, it was developed by Collins in 2003. And so basically the first part is that there's this sequence of like special functions called WG, which are defined on the symmetric group, like on SK, that have this property where the integral over UD of like this kind of product of matrix entries is equal to the sum of the values of WG. And so the sum here is over pairs of permutations. And then there are these two like compatibility conditions, like for each permutation. like with indices of the matrix entries. And I'll kind of I'll give an example in a couple slides to illustrate how this sum works. But for now, the point is that you know, these integrals are basically encoded in these functions on the symmetric group. Yeah, so, and then the other half of this, you know, sort of step one is that, like, we want to have a concrete description of what these functions WG are, right? And so this is also provided by Collins in the same paper. So basically WG, well, so like a special feature of WG that I didn't mention in the slide is that it's is that like WG of a permutation only depends on the conjugacy class, or you know, the cycle type of that permutation. And so you know, just by like representation theory of finite groups, that means that WG is going to be a linear combination of these irreducible characters of SK. So you know, this is again just kind of basic representation theory that the irreducible characters of SK are labeled by integer partitions. So the sum here is over integer partitions lambda of K, and then there's like a length constraint here. And the point here, though, is that the coefficients have this combinatorial form. So like this, you know, so-called dimension of lambda, this is, you know, kind of a fancy way of writing the number of certain Young tableau with this shape lambda. And it doesn't really matter what this is for the purposes of this talk. My point is just that, you know, there's a straightforward combinatorial formula for this. You know, down here is just a factorial. And then there's this, you know, this is basically, so this is called a Schur polynomial. And it has certain arguments. Like it's the Schur polynomial where you set the arguments to just one. But again, like it doesn't really matter what exactly this is for the purposes of this talk. The point is just that there's this, again, kind of simple formula for this in terms of like the combinatorics of integer partitions. And so if you want to, I mean, if you're interested in either of these theorems, there's a great survey that Collins wrote with, I guess, last year, and you can find it at this archive link. So if you want to know anything about this, this is a good place to start. But I'll just give like a simple example here of how this works to kind of illustrate this sort of reduction from analysis to combinatorics. Right, so yeah, so like this is kind of like a simple, you know, product of these matrix entries. So here, like the indices are right, so that there's like there's four multi-indices, right? There's an I, a J, an I prime, and a J prime. So the first three are just, no, this should be J prime, sorry. Right, so these three indices are just 1, 2, and I prime. No, wait, this is I prime. This is J prime. Yeah, and so then this is 2, 1. So, right, in terms of this sum over pairs of permutations, you know, we have two constraints, right? One of them, so this I equals I prime composed with sigma. if you work out what this means in terms of these two multi-indices, this makes this forces sigma to be 1, right? Basically because like I and I prime are the same, right? So this condition is forcing sigma to just be the identity permutation. And then the second constraint, so the one on the bottom here, right, so if you work out what this means, it's going to force tau to be the permutation 1, 2. Right, so then if you put this back into like the right-hand side here, right, so this is just going to be the function WG evaluated at the permutation 1, 2. So this is basically the first theorem that I showed. Like this is what it means in this case. And then when you apply the second theorem, which I'm not going to do in detail, I'll just copy down what the result is. Basically, the second theorem gives you like a combinatorial formula for the values of this function. So it turns out that this is -1 over d times d minus 1 times d plus 2. And this is just copied from a reference table, but you can compute it directly using this formula. Basically, like this rational function in D is going to come from this polynomial in D. So this is just kind of a short illustration of how Weingarten calculus works. This is kind of like a pretty short computation for something that you might not expect to be easy to compute. So with this example, I hope I've kind of conveyed how Weingarten calculus is kind of reducing the analysis to combinatorics. And so once we've used this in general for for these integrals that we wanted to compute, these. The dependence, so like basically the formulas for this come down to this kind of weird looking expression. And so the first thing you might notice about it, especially based on how I did the coloring, is that it's a lot like a determinant, right? Like you on the outside, you have this sum over sigmas, and then part of the summand is this product of of matrix entries, right? Like where this is I and this is J, right? So it looks kind of like a determinant, but instead of just having a sign here like you would in a determinant, you have all this extra stuff, which I'll explain in a minute, like what these sums are. But yeah, the point here is that you have some more complicated information about this permutation sigma than just its sign. So just some context for this sum is that these variables x, these are certain scalars which are supposed, so like there's a bunch of sums on the outside, right? And so these x, like xi's, these are meant to range over subsets of the diagonal entries of A. And then also there's a fixed integer partition mu, which is also coming from the outside sums. Yeah, so this is kind of like fixed information for each copy of this expression that appears. And so I just kind of want to explain what this stuff is, like basically what these two sums are. And so I've kind of reproduced them here. Right, so we have this fixed partition mu. And so the outer sum is over set partitions of like 1 through k, whose I guess you could say block type is mu. So like basically mu is like the sizes of the blocks of the partition pi. And then for each of these partitions pi, you have this inner sum of permutations that leave the blocks invariant. So that's what I mean by this tau less than or equal to pi. This means that tau tau leaves the blocks of pi invariant. Right. So I have this sort of concrete example. So like here k equals 8, and the sort of fixed integer partition is 4, 2, 1, 1. So this is a partition of 8. And then pi here is just some partition of 1 through 8, which has like whose blocks correspond to this integer partition, right? It has a block of size 4, it has a block of size 2, and it has 2 singletons, so 4, 2, 1, 1. And so this inner sum, this sum over permutations that leave the blocks here invariant, this has indices like, so some of the permutations here that appear would be like 1, right? Because this leaves all of the blocks invariant, just trivially. 1, 4, 3, this leaves all of the blocks invariant, right? Because 1, 4, and 3 are all in the same like 4-element block. 1, 8, 3, 4 times 6, 7. This leaves all of the blocks invariant, right? It leaves this one invariant, and it leaves this one invariant. And so the key observation about this sum that makes it possible to handle is that each of these inner sums is actually a sum over a subgroup of SK. So like this property of being invariant, like of leaving the blocks of pi invariant, actually determines a subgroup of SK. And then it turns out that this outer sum is summing over the conjugates of this subgroup, like in the interior. And so basically what's happening here is that you're summing, like this outer sum is summing over conjugates of what's called the Young subgroup of SK. And so this is a subgroup that's very well studied in representation theory. And so we can just use that to basically make these sums go away, and turn this into something more familiar. So basically the proposition here is that if you have 2 partitions of K, then this sum here, so like this is the sum, that I was talking about here. This sum is actually just a scalar multiple of the character labeled by lambda at the permutation sigma. So basically the effect of all of this complicated summation is really just a scalar multiple. And so moreover, these constants are easy enough to describe. basically they depend on a certain kind of ordering of the partitions of integers called the dominance ordering, and sort of the combinatorics around this ordering. In many cases, these constants are zero, and in the non-zero cases that are relevant for this computation, there's a simple formula involving factorials and binomial coefficients. So this is actually quite easy. Well, maybe not easy, but it's possible to handle. And so again, the idea of the proof is that this big sum, this big pair of sums is over conjugates of this so-called Young subgroup labeled by mu. And this is very well understood in the representation theory of SK. So you can just open up a textbook on this subject and use the results from there. Right, and so the point of all this is that the dependence of this expected characteristic polynomial of this should say this should say y1 a u b u star plus y2 u b u star a. I mean, this is also true, but we want to work with this for now. Right, so the dependence of this expected characteristic polynomial on A is only through expressions that look like this. So it's a sum over some permutations of with values of like a character of SK, and then this kind of like determinant like product of entries. And so this kind of thing has a name. It's called an immanence of this matrix. So the definition here is that the immanence of a k by k matrix X with respect to a partition of k is defined like this, right? It's like a determinant, but instead of the sign here, you're using an irreducible character of SK, which is labeled by lambda. And so this is a common generalization of both the determinant. So the determinant is the case where lambda is the partition with one column, and then the permanent is the case where lambda only has one row. Right, so yeah, this is something that has been studied to some extent for quite a long time. But the thing about immanence is that like they're very hard to compute in general. And so basically the last step is in the argument here is to realize that we don't actually need to compute immanence in general. We only care about immanence of this very specific kind of matrix. And it turns out that immanence of this kind of matrix can actually be computed in some reasonable way. Right, so this is the last step. Computing the immanence using results of Goulden and Jackson from the 1990s, which describes immanence in a useful way. Right, so to describe these immanence, this result of Goulden and Jackson is using these symmetric polynomials called Schur polynomials. So I'll just kind of like review what these are. So this is probably the most concrete down-to-earth definition of these polynomials. So you fix a partition of K, and you define S lambda of like these K arguments by summing over certain tableau with shape lambda. So here the notation is SST of lambda. This is the set of so-called semi-standard tableau with shape lambda. So semi-standard means the rows are weakly increasing and the columns are strictly increasing. So you can see a bunch of examples down here. And then like each of these exponents here is the number of entry, like omega I of tableau T is the number of times that I appears in T, right? So I think this is illustrated pretty well by this example down here. So this is the case where lambda is the partition 2, 1, which is a partition of 3. So, this is a partition that has this Young diagram. And so a semi-standard tableau is just filling the boxes of this Young diagram with ones, twos, threes, in a way where the rows are weakly increasing, right? So like 1, 1, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3 are the possibilities. And then the columns are strictly increasing. So in the columns, you can only have 1, 2, 1, 3, or 2, 3. Right. And so for like basically these are the things that are being summed over here. And then for each one of these, indices for the sum, I've written out what the what the monomial is here. So here, there's 2 1s and 1 2. So you get an alpha 1 squared times alpha 2. Here there's 1 of each. So you get a alpha 1 times alpha 2 times alpha 3, and so on, right? So S21 is just summing up all of these monomials. Right, so the theorem of Goulden and Jackson is basically, maybe I don't have time to go into a lot of detail about this, but basically what it's doing is reducing computations of these imminents to computations of certain Schur polynomials. And so if you kind of understand what all of this notation means, you might think that this is just another really complicated expression, which it is. But the key thing is that we only care about a particular kind of matrix. So we only care about this kind of rank 2 matrix where the entries are y1 xi plus y2 xj. Right, so this has rank 2. And so there's only we only need to worry about 2 non-zero eigenvalues, right? So there's only 2 non-zero arguments in this Schur polynomial. And so that makes this Schur polynomial much simpler to compute than it would be in general. So there's this lemma basically doing that computation. So if you have non-zero alpha and beta, and then all the other arguments are 0, then this polynomial will have this form when the length of lambda is at most 2, and then otherwise this polynomial will just be 0. So here you can kind of see how this simplification goes, because if your lambda has length 2, this lambda does, so here lambda is 3, 2. You can imagine that there are lots of semi-standard tableaux which have this shape, but the ones that only have entries 1 and 2 are actually, there's actually only 2 of them. So this Schur polynomial is much simpler in this special case of rank 2. And so the key point is that in the case of the commutator, so this is when y1 equals 1 and y2 equals -1. So the matrix we're working with is just xi minus xj. Then it turns out that not only do we only have 2 non-zero eigenvalues, but those 2 non-zero eigenvalues are actually the same except for a sign. One is minus the other. And so then this non-zero expression for the Schur polynomial, it reduces even more to something that doesn't actually depend on lambda, except through this sign, right? Otherwise, it's just depending on this matrix, right? Like there's this is like one of the eigenvalues of this matrix, basically. And so you have this reduction from an imminent to a sign times a permanent, which is much, much simpler. And you can just directly compute what the permanent is. And so basically, once you've done this computation, then you can basically just go backward through all of the reductions, and you'll end up with a proof of the theorem that I presented at the beginning. So really, like, all the work is in the reductions, and then at the end of the day, it's just a very straightforward computation of the permanent of a particular matrix. Right, so in the last few minutes, I want to talk about this question of real rootedness. So this is related to the question from earlier, I think from Jorge. Right, so the question is, if you have two, like real rooted polynomials, P and Q, then is this expression for the commutator, is this real rooted? And so I've done a lot of computations in Sage with random polynomials, which strongly suggest that this is real rooted. I don't know how to prove it, though. That's still a work in progress. But the one sort of insight that I've had together with Daniel Perales and Rafael Morales is that it seems to be related to hypergeometric polynomials and when they're real rooted. So there's this recent preprint by those two and Andre Martinez Finkelstein, which is basically about how hypergeometric polynomials connect with finite free convolutions. Like basically they have formulas for like box plus and box times, where the polynomials are like hypergeometric. And this preprint should be relevant. So again, this is a work in progress, trying to figure out if we can prove that this is real rooted. Right, so another thing that I should mention is this polynomial Z. This is, right, so like if you remember, this is the kind of like universal polynomial here that only that does not depend on P and Q. So the way that I wrote it down in my paper is essentially like this. So like it's a very kind of concrete polynomial, but it's a little bit, opaque what it actually means. So I just put a picture here of its roots. So the roots are, they do seem to be real. This is when D equals 20. And so in terms of explaining why this has real roots, I think what can be done is you can rewrite this in the form of a hypergeometric polynomial. Specifically, I think it should be a 4f3, if I mean, like in case anyone knows what that means. And then there's a bunch of normalizations, of course, but yeah, so this is a hypergeometric polynomial, which is basically kind of like playing this role in the commutator, kind of similar to like the zeta that appears in like if you know this paper by Nika and Spiker from '98, they have this zeta power series which plays a similar role as Z does here, but this Z is a lot more complicated than that. So yeah, that's what I wanted to say about real rootedness, and I think I'll actually stop there. So yeah, thanks for listening.